talked about is the solutions to Maxwell's equations in free space, for which we said there exist electromagnetic wave solutions. But we haven't talked about where those waves come from. We haven't talked about radiation of electromagnetic waves by prescribed sources. So when we talk about statics and quasi-statics, we spend a lot of time saying here's a given charge distribution, here's a given current distribution, here is the field associated with that. But we haven't solved Maxwell's equations for the fields associated with time-dependent sources beyond quasi-statics. Okay? So that's what we want to talk about. We're going to be talking about for the next few lectures. So to do that, let's think about, firstly, let's just first think about the wave equation. Let's just for the moment think about it for a scalar field. Let's forget about the vector nature of the wave for the moment with the source. So we have wave equation with some wave propagation speed c, would be the speed of light, equals now some source. And we have looked at the homogeneous solution where this was 0, but now we want to look for the particular solution. How do we do it? Guess, maybe. Be a hard, you might guess, but it's pretty hard pressed to guess.
I mean, you could break your source up into like Fourier some sort of basis.
Yeah, we could do something pretty close to that. What we see, this is the same kind of problem that we've discussed before. I mean, suppose we didn't have this d by dt squared here, right? Then it would look like the Laplace equation, Laplace equals that's what we call Poisson's equation. And we solve that by looking for the Green's function, which is equivalent essentially to what you're saying. So the Green's function is the solution when the source is a delta function. So instead of breaking up into Fourier components, we break, as we've discussed, we break up the source into delta functions. So in this case, our delta function is a delta function in space and time. So at time t prime and at position x prime, the source goes boop, and then a wave is emitted. Okay? And there we've said that the source itself can be thought of as a superposition of those weighted by different levels of boopiness. Okay? So, what is the solution? If I have wave propagation, all of a sudden, I won't say it again, but you get it. What's going to happen when you have this impulse? It's like dropping a pebble into a pond. Right at that point, right at that instant, you will get emission we expect from an impulse response. In this case, should give us a spherical wave. So what we would expect is right if the source just goes off right then emitted from that point is a spherical wave into the, would be a circular wave or a cylindrical wave. So that's what we expect to see, and we're going to see that is the Green's function. And then if we had an arbitrary source, which is a superposition of impulses at different positions and different times, then our general solution will just be the convolution of the weighted strength of the source with the Green's function associated with the impulse response, the spherical wave. So we seek the solution to the wave equation with that source. That's the Green's function. Okay? And we can just change variables. We'll call this capital X and this tau. And then the derivatives can be shifted. So this is now the derivative with respect to capital X. D squared by d tau squared, g x and tau equals. Okay. So, how do we solve for the Green's function? Take the Fourier transform. Thank you. So we just take the Fourier transform. And thus we get minus k squared plus omega squared over c squared d tilde k and omega is equal to the Fourier transform of this, which is so we have now the Green's function for the 3D wave equation is that. Okay? And so now to find the Green's function in space-time, we need to take the inverse Fourier transform. Isn't it nice to solve a differential equation in Fourier space? That's lovely. I have to integrate over omega, integrate over k. I have a 2 pi for each of those. Plug in this guy. C squared, I'll write it this way. And now we just have to do that integral. How are we going to do that integral? Well, we can use the analytic continuation that we discussed when we were talking about linear response theory to integrate this by extending into the complex omega plane, and then use the theory of residues to determine the value of that integral, particularly the integral over omega. Okay, so let's write this in. Integral d omega. So, what we discussed here is that this function is equal to, well, let me say this like this way. The integral over omega of dk of omega tau is equal to the integral of the closed contour in the complex plane in the upper half plane when tau is greater than 0, and in the lower half plane, oh, it's got to be this, when tau is greater than 0. Sorry, I got this backwards. Okay. So, what do we, well, causality would tell us we expect, if we're talking about what the wave is due to sources, then what we expect is that this Green's function is causal, if that's what we're interested in. We want to know what is the wave that we see at some time due to what the sources were doing at an earlier time. They can't depend on what the sources were doing in the future. But remember, of course, that this integral over here is related to 2 pi I times the sum of the residues in upper half plane of the complex omega plane. And this is minus 2 pi I times the residues in the lower half plane. And the residues are related to the poles. So what we discussed when we were talking about linear response theory is that a causal response will have its poles in the lower half of the complex omega plane. But where are the poles of this function? Well, the poles are on the real omega axis. That is to say, if I were to look at this, I'm going to We have a pole here and a pole here. So the causality is not in the wave equation itself. In fact, it's completely ambiguous. These poles are not in the upper half plane or in the lower half plane. They're right on the border between those two situations, which means that there is a causal solution and an acausal solution to the problem. We can move the poles slightly off the plane by some amount epsilon, in which case we would get the acausal solution, or move them slightly off with negative omega along the imaginary omega axis, and then take the limit as epsilon goes to 0. But these two different limits give us two different Green's functions. We call them, there are two different Green's functions, which we are traditionally called G plus and G minus, which I will write in the Fourier domain, would be equal to so what I'm doing is I'm moving the poles, giving them some imaginary part that I then take the limit as epsilon goes to 0. If I have a negative imaginary part of my pole, it's called the retarded Green's function, retardation. And with the other sign, it's called the advanced Green's function. Now you might say, this advanced Green's function is not physical, so why the heck are we even bothering with it? Well, indeed, but it depends on the context. Both of these you may be familiar with, maybe you've seen it depending on what you studied in your advanced quantum mechanics course 522, appear in scattering theory. In scattering theory, one typically is thinking about a situation where what we have is some incoming wave and some outgoing wave, and we have some scatterer in the middle, having to do with asymptotic boundary conditions. And if I'm wanting to say I know in the past the wave was something and it's coming in, then really that problem is kind of a time reverse problem. It's really the advanced Green's function that tells me how that would have happened. And then, of course, the outgoing wave is related to the retarded Green's function. So they have mathematical meaning, which is appropriate for certain physical contexts when, depending on the boundary conditions that I'm thinking about. And the wave equation allows me to solve for both kinds of Green's functions. Okay. However, here we're interested in a very particular problem. We're interested in the waves created by a prescribed source. So for that problem, so this would be related to the those two Green's functions. The S wave, the S matrix is related to some combination in to out. which depends on both the incoming and outgoing waves, but again, it's retarded. But here, for our case, we are interested in the wave radiated by a prescribed source. And that means that we're interested in the causal solution. The retarded Green's function. All right. So, that means that the retarded Green's function as a function of now in position space and time is equal to the limit as epsilon goes to 0 of this integral with this set of poles. All right. So our poles are here, and so we then just write this as minus 2 pi I times the sum of the residues. It's minus because this is a contour with the left-hand rule. Otherwise, it would have been plus 2 pi I. All right. So, this then is equal to, when I put in the poles and the residues, and then take that limit as epsilon goes to 0. Well, I guess I might do the ik dot x. Sorry. I get 2 pi I CQ minus sine CK tau over K e to the I K dot x. Okay, so that comes from the two poles, the one at CK and the one at minus CK, which gives us either the I CK tau and the minus I CK tau, which gives me the sine function. All that algebra. Okay, so now we just have to do this integral, and the way you do it is similar if you go back in time to when we were looking at the Green's function for the Poisson equation. We take the direction x to be the polar axis with which we define polar coordinates for k. Yeah?
So the epsilon's in there, did you just take the limit?
I already did.
Okay, cool.
I already did. I mean, really, in I shouldn't have two of these, sorry. I mean, really, it's still there, it really gives you a convergence factor because this integral doesn't really converge.
Okay.
But it converges to a delta function, so I'm not going to bother with
Okay,
it.
cool, cool, cool.
So, all right. So we turn this into we write this in terms of spherical coordinates, dk times k squared d omega. Do this integral, and we get the following. I wrote the algebras here in the notes. It's boring. And what we get is the causal solution is c over 4 pi delta function magnitude of x minus c tau divided by the magnitude of x. And this is my retarded Green's function. All right, so what does this then tell us? Well, as we said, the solution, the particular solution then, to the wave equation is given by the convolution of the Green's function, in this case, the retarded Green's function, with the source. And we just found that Green's function, so we can write that out. That's equal to minus c over 4 pi integral d cubed x prime dt prime, the Green's function. There's no more fiddle on this because it's in space. Lets you delta function magnitude x minus x prime minus c t minus c plus c t minus t prime plus t prime divided by the magnitude of x plus x prime. Okay? We can, I should have done it here, factor out a c from the delta function. Remember that a delta function with a constant is the same as 1 over the constant. It's the positive constant. Right? That rule. So I'm going to factor out. Let's see. It over here. So we then this gets multiplied by the source. So now we can do the integral over t prime, and t prime is equal to t minus this. So this is equal to the integral over x prime, the source at x prime at t prime is equal to what is called the retarded time, which depends on t and the distance between x and x prime over x minus x prime. So I have defined the retarded time is equal to t minus x minus x prime over c. And this is a very important solution. So let's interpret some of these solutions that we have found. First of all, let's look at the Green's function that we found in the time domain. The Green's function is 0 everywhere except when tau is equal to the magnitude of x over c. And then it falls off like 1 over that magnitude. So the Green's function is, if I now introduce a kind of space-time diagram, and since I can't draw 4D, I can barely draw 3D, and let's try 3D for a moment. The Green's function, as far as the has this light cone structure. That is to say, the Green's function is non-zero only when Ct is equal to the magnitude of x, which in this case is just writing this in 2D, it's magnitude of x squared plus y squared. So this is our outward propagating spherical wavefront that comes from, in this case, circular wavefront, that is being emanated from this point, just like we imagined when we dropped the pebble in the water. What does this solution tell us? Well, what this tells us is that what we see, what wave amplitude exists at position x and time t depends upon what the source was doing at an earlier time. And that time is none other than the time that it took the wave to propagate from its emanating point at x prime to the point of interest, x. So this is the time it takes to propagate. So what this says is the following. Let's think about, this is this kind of space-time diagram where for the moment I'm going to restrict our attention to one spatial dimension and then time. Okay? So here I am, me, at this point, wanting to know something about what wave amplitude I see at this position, at my position at that time. What I see depends upon what was going on in my past. And moreover, it depends on my past that propagates to me at the speed of light. So if these are supposed to be lines that have a slope of 1 in these units, this, as you know from your previous studies, is known as the backward light cone. So these are all the light signals that could have gotten to me at my position at my time. So if there is some charge moving around here, then when it crosses my backward light cone, that is a sphere, that if it emits a wave, that can contribute to what I see right here. So this is the source at position x prime at position p prime. This is its world line representing its trajectory in space and time. When it crosses my backward light cone, it can contribute to the signal that I see. The signal that I see at my time t depends upon what this source was doing at an earlier time, if it crossed my backward light cone. If it's in my past, then it could go back to my backward light cone over here. It would contribute to what I see at this time, but it won't contribute to what I see at the present. Of course, it also can propagate into my future. Okay? So the total signal that I see depends on the superposition of all of the sources doing whatever the heck they're doing, and whenever they cross my backward light cone, according to the retarded time, they can contribute to my signal. And the strength falls off like 1 over the distance, as a spherical wave must. We studied the spherical waves in homework. Okay? Now we can see this maybe even more explicitly as a spherical wave if we think about this for the case where our source was oscillating with a fixed frequency, harmonic frequency. So for a harmonic oscillating source, so let's say that the source as a function of the new time is the real part of some complex amplitude e to the minus I omega t. Okay? So it has some fixed frequency. Then the complex amplitude of the wave that I see so again, the wave that I see will have some complex amplitude. The wave will oscillate at that frequency, at the frequency of the source. So I can now plug this source into this problem. So that says this is equal to the real part of minus 1 over 4 pi, the integral over all space, the source complex amplitude at that space, times e to the minus I, the retarded time. The retarded time is t minus x prime over c divided by minus x prime. Okay, plugging in that ansatz for the time dependence of the source into my convolution integral. So this is equal to the real part. So the wave amplitude I see is the real part over 4 pi, the integral d cubed x prime e to the I omit k where k is omega over c. So what we see here is that the complex amplitude of this wave is a superposition of spherical waves. Remember the spherical waves? This is what we derived when we looked at that problem in homework. They propagate out, in this case, centered at x prime, where the wave fronts are on the surfaces of spheres, and the amplitude of the wave falls off as 1 over the distance from the center of a radiating source. And the strength of that spherical wave depends on the strength of the source at the point of the source. And the total amplitude I see is nothing more than a superposition of spherical waves. Isn't that cool? Does that work out real nice? Yeah.
Is that where they use the latest wavelength principle?
Indeed, they do. Yep. Now, I don't think Huygens got it from this, but this is the foundational mathematics behind it. Huygens didn't have that, so. All right, so, I just love that. It's turned out so nice and pretty. All right, let's go to the front board because we need to start now. Which is, okay, so now we have talked about I don't know why I was biased against that side, we've talked about this as just a mathematics solution. Given a wave equation and given then a source, what is the particular solution? What is the Green's function? What we want to now look at is how this helps us find the solutions to Maxwell's equations with sources. So what we're looking at now is the general solution to Maxwell's equations with sources. So let's go back and remind ourselves what we had in statics. And now we're going to return to the microscopic Maxwell's equations, although we could do the similar thing for the macroscopic equations with our D's and H's and all that stuff as well. So for statics, we had Gauss's law, the law that shall have no name, Faraday's law, well, quasi-statics. No, I'm sorry. Let's go back. Let's talk about statics. So this is the Faraday's law for statics, is del cross E is 0, and Ampere's law. Okay? How did we solve these equations? Suppose there you are back on your favorite desert island. You got Gilligan and Marianne, but not the professor, and you got to solve these equations. What are you going to do? Well, the way we did it is the equations that don't involve the sources allowed us to transform the fields into potentials, right? So this equation told us that B itself must be the curl of another vector field that we call the vector potential. And the fact that the curl of these static field was 0 told us that the electric field itself was the gradient of another scalar field that we call the scalar potential, and by convention of its relation to potential energy, we put the minus sign in there. Okay? And then we plug these back into the equations with the sources. And these two together told us then that the Laplacian of phi was equal to minus 4 pi rho. And the combination of these two equations together told us that the gradient of the divergence of A minus the Laplacian of A was equal to 4 pi over C j. And then we solve for the potentials. And then once we have the potentials, then we can find the fields by taking the appropriate derivatives. And how do we solve these equations? Well, firstly, we had the gauge choice. We said the divergence of A can be chosen any way we like because it's completely irrelevant to the physical forces, and for statics, we chose it to be 0. So we ended up with, I'll leave that there. In statics, we ended up with these equations for the potentials. And how did we solve it? With the Green's function, right? So we had the Green's function for the Poisson equation. And we found that some months ago now, and that was equal to -1 over 4 pi x over x pi, or magnitude of x minus x pi. And so the solution that we have in this case in statics is equal to the Green's function involved with the source, which is equal to the solution we could have written down by heart, Q over R is the potential. And similarly, when you do that convolution for this choice of gauge, we have that solution for the effective potential. So that's the formal solution to Maxwell's equations in statics. And this is just another statement of Coulomb's law and the Biot-Savart law, written in terms of potential. All right, hint, how do we solve this now for the general Maxwell's equations when we now include dynamics? So now let's look at the general case. So now, Maxwell's equations are modified to include possible time-dependent sources and thus time-dependent fields. How are we going to solve these equations? We're going to do it exactly the same way. We express the fields in terms of the potentials. We plug those expressions back into the equations that involve the sources, and then we'll use the appropriate Green's function to solve for the potentials. And once we have the potentials, we can get the fields. So, as before, even once we go to the dynamic case, D, it's still related to the curl of a vector field because its divergence is 0. So that's still true. And we still have the divergence of A is arbitrary and can be fixed any way we like according to a gauge choice. All right? However, Del cross E ain't 0 no more. So that means that E is not just the gradient of a scalar field, unless this happens to be 0. However, if we look at this equation, then if I substitute in B is the curl of A, and change the order in which I differentiate, then what we see here is that the curl of the combination of E,
Wait, shouldn't it be del cross, del cross?
I plugged in here B is del cross A. So there's only one cross. And then there's that one derivative. So, this indeed is correct. So what that tells me is that this combination itself is irrotational. It has a curl of 0. And thus that combination together can be written as the gradient of a scalar, which by tradition is minus phi. And so we have in dynamics a slightly, and in fact very important distinction. The vector potential, as we will see, plays a much more central role in dynamics. And E and B are both related to the vector potential. In this case now, we have this relation. So, we have, again, potentials. However, we have to think about this business about gauge. So what we said here, gauge invariance, if I make a transformation by adding to A the gradient of some other scalar field, lambda, which is called the gauge field, then because B is the curl of A, and the curl of a gradient is always 0, the magnetic field does not change. So one can fix the divergence of A by an appropriate choice of the divergence of this, or the Laplacian of this field, satisfying an appropriate Laplace or Poisson type equation. What about the electric field? Well, if we're going to change A in this way, E wouldn't stay the same, unless I also change the scalar field. So I have to, the gauge transformations now involve some transformation of phi going to some new phi prime. In fact, we can see what phi prime must be, because if E is equal to minus, or goes to minus the gradient of phi prime, d by dt A plus the grad of lambda under a gauge transformation. If A changes by that amount, and phi is some new phi, well, this then is equal to plus 1 over c d lambda dt plus 1 over c. So in order for E to go back to itself, which it must, because the physical forces depend on E and B, and a gauge transformation cannot change that, then we must have that phi prime equals phi minus 1 over c d lambda dt. So there is a gauge function lambda, which is a function of position and time. And if I shift A and phi, the vector potential and the scalar potential, in this way, then I don't change the physical forces. And I can choose those in the way I like. Now, in statics, although it's been erased, we said that the standard choice was to choose del dot A is equal to 0. In dynamics, there are kind of two standard choices. So the first choice is what's known as Lorentz gauge. And in the Lorentz gauge, we choose A to have the divergence of A to be related to minus 1 over C d phi dt. That's called the Lorentz gauge because this condition is the same in all inertial reference frames. So if we do, as we'll discuss, hopefully, maybe during finals week, Lorentz transformations, then this gauge condition is Lorentz invariant, and that's called the Lorentz gauge. Otherwise, in a different reference frame, we have to do a gauge transformation, and we can't keep the same gauge in all reference frames. So in relativistic dynamics, it's quite often the standard gauge. You just choose the Lorentz gauge. But it's not the only choice. There's another gauge, which is known as the Coulomb gauge, also known as the transverse gauge. Which goes back and just says, let's just keep A to be divergences. And the transverse function, so to speak. This gauge is very standard in radiation theory, and in fact is the standard choice in non-relativistic quantum optics. We'll see that. All right. So, we have the relationship now between the fields and the potentials. So in order to, what we're ultimately after is how do the sources produce the fields. So in the same way that we did in the static case, we now plug these equations back into the Maxwell equations that involve sources, Gauss's law, and the modified Ampere's law. So let's do that. So, del dot E is equal to the divergence of minus the gradient of phi minus 1 over c d a dt. Once again, in these Gaussian units, the vector potential and the scalar potential have the same units. So this is a distance, that's a distance. Is equal to minus, I'm sorry, is equal to 4 pi rho. Or minus Laplacian of phi is equal to minus 1 over over C d by dt. The divergence of A, 4 pi. Okay? And del cross B is equal to del cross A, which everyone knows is the gradient of the divergence of A minus the Laplacian of A, and that equals 4 pi over Cj plus 1 over C d by dt of E, which is minus the gradient of phi minus 1 over C dt. So, what do we get? We get what am I doing? Oh yeah. We get here then the Laplacian of A minus 1 over C squared by dt squared of A is equal to minus 4 pi over C j plus the gradient of del dot A plus 1 over C phi. All right, so we just took these definitions of the fields in terms of the potentials, and we plugged them back into the source equations and the equations. Now we have to choose our gauge. Let's start with Lorentz gauge. So we choose a Lorentz gauge. Del dot A plus 1 over C d phi dt is equal to 0. So that means we can plug that in for del dot A is equal to minus 1 over C d phi dt. That gives us here a plus d by dt squared 1 over C squared. So in the Lorentz gauge, we get del squared minus 1 over C squared d by dt squared by x and t equal to minus 4 pi rho. And this is equal to 0 in the Lorentz gauge. So in the Lorentz gauge, the vector potential satisfies the wave equation with sources. So in the Lorentz gauge, what we find is that in electrodynamics, the scalar and vector potentials satisfy none other than the wave equation with sources. And we just solved it. There it is. So we know the solution. It says that to find, we use the retarded Green's function because we're looking for causal solutions. We convolve that, and there it is. Luckily, not erased yet. So the solution is the scalar potential of the function of time. Well, minus 1 over 4 pi cancels that. Integral over the sources. The source, but not at the same time, but at the retarded time. which is a function of time and the distance between the point of observation. And the vector potential is the same kind of integral over the current density at the retarded time. And that's it. It looks just like the solution that we wrote down in the static case, but not quite. It has this very important difference in that the potential I see at time at position x and time t is not related to what the source is instantaneously at that time, but what the source was doing at the retarded time. And similarly for the vector potential. And that's really important because, as we'll see, that seemingly small difference of this one subscript on this allows for electromagnetic radiation, energy that can propagate away to infinity away from the sources. Now, to conclude, I want to just, because I think it's interesting and sometimes useful. What do these solutions look like if I had chosen the Coulomb gauge? We could have done that. There's nothing that insists on me choosing the Lorentz gauge. I could choose the Coulomb gauge. So let's look at the solutions in the Coulomb gauge. At the end of the day, the physical fields can't depend on the gauge choice, but the potentials look quite different. So, let's see, let's go over here. In the Coulomb gauge, del dot A is 0. So that's 0. So we get del squared phi is minus 4 pi rho at x. And what about the vector potential? Del dot A is 0 here. So I get del squared minus 1 over c squared d by dt squared of A is equal to minus 4 pi over c, something I'm going to call jt. Where jt is equal to j, and if del dot A is 0, then it's minus minus 1 over c gradient over 4 pi c. All right, so why am I calling this JT? Well, let's look at what the divergence of JT is. That's equal to the divergence of J minus 1 over 4 pi C, the Laplacian of d phi dt, or d by dt, Laplacian of phi. But the Laplacian of phi in this gauge is minus 4 pi rho. So this is equal to del dot J plus d rho dt. But what is that? Zero, because charge is conserved. So this is the part of the current which is transverse. In other words, perpendicular to the K vector. If this was kind of a plane wave. And that's true because if I take the divergence of this, del dot A is 0, and then this is 0. So that's consistent. This divergence is on both sides. What is the solution to these equations? Well, this equation is kind of weird. Notice there's no d by dt here. This looks like, exactly like the static problem. T is just a parameter here. T, there's no derivative with respect to time 1. So the solution we have in the Coulomb gauge, or sometimes known as the transverse gauge, doesn't have the retarded time in it. It has the instantaneous time. This solution does have the retarded time, but in a way that depends on this funky transversy thing. So this says that A is equal to the integral J transverse T retarded. So what the heck is going on here? Well, it's a little bit weird. It seems like something is superluminal because the field, or the potential at time t depends on what the source was at some other point in space at the same time, even if they are space-like separated points. Well, that's not really true. It's true in terms of what the potentials are, but it's not true in terms of what the fields are. The fields are still causal. They came from the causal, we still use the causal Maxwell's equations. But we've broken it up into a weird way. Notice this is nothing more than the local Coulomb field, why it's called the Coulomb gauge. In other words, if I just had a source that was a charge density at some time t, and I asked you what is the electrostatic potential about that, this is what you plug in, but with that being the source at that time. This division is useful if we want to divide the part of the field that is near field, static in nature, from the far field, radiation nature. We're going to discuss that next time, this notion of the near field and the far field, the static and the radiation. But in some sense, as far as the electric field is concerned, the electric field, which we said was related always to the scalar and vector potentials this way, this part, which is the gradient of phi, is kind of the electrostatic part. And this part is the radiation part in the Coulomb gauge, which is why we like the Coulomb gauge. Because then we only have to deal with the vector potentials. And when you do quantum electrodynamics, if you do that, QED, then we always just deal with the vector potential, because that's the part that has to do with the photons. Whereas the scalar potential, that's just that's something kind of weird and different. All right. Okay, so just to summarize, what we're actually into, it doesn't matter which gauge you use, at the end of the day, they'll be the same thing. It's sometimes easier to work with the Lorentz gauge, and that's what we'll do. So we have the formal solution. And you remember what we did in the static case. Once we had a solution, we looked for multipole. And so we're going to now look at multipole radiation, electric dipole radiation, magnetic dipole radiation. All right?